All right, let's continue our discussion. We started with the concept of mutually exclusive, and here's one example. If you draw a card from a deck of cards and event A is defined as getting an ace and event B is defined as getting a king, these two are mutually exclusive. You will never have ace of kings, all right? There is no such a thing. However, that is not the case if I define event A as getting a heart and event B getting a king, right? Because there is a king of hearts. Let's move on to the next concept of union. Union of A and B is an event that its members are part of A or part of B, all right? So this event contains all members of A and B. Now, probability, how do we define probability of A union with B? Probability of A union with B is defined as a P of A plus P of B minus P of that intersection. Why that intersection? We subtracted because we double counted it, right? Here is one example, all right? If we are looking for, again, event A is getting a heart, event B getting a king, P of their union is going to be P of heart, which is this whole area right here, plus P of B, P of king, probability of king, right? So you see that I'm double counting that king of heart. So in order to adjust for that, I need to subtract that one time. That king of heart happened to be the intersection of hearts and kings, all right? So that justifies this formula of P of A union with B equal to P of A plus P of B minus P of A intersection with B. Now, this is practice for you. Try to recognize, try to mark any of these that you see here with whatever we have learned so far. All right, so if A and B are not, they don't have anything in common, so their intersection, their union is going to be P of A plus P of B. If they have intersection, then their probability of A union with B is going to be their sum minus intersection. This is a problem for you to work on it yourself, so I'm going to skip it for the sake of time. Let's move on to the very important concept of conditional probability. So far, whatever we have done so far in terms of probability calculation, everything that we have done so far, we have assumed that we don't have any additional information. Oftentimes, after observing, after getting some information, you need to go back and adjust your probabilities. All right, we do this in our head all the time as well, right? So, but we don't call it conditional probability. You look outside and you see that it's raining heavily. Well, you were going to go out 5 minutes from now. You automatically adjust in your head that condition on the fact that it's raining right now. There's a high chance that it is going to also rain 5 minutes from now. So if you had that plan that earlier, I'm going to go out and enjoy the sun, so now you have to adjust the probability of sunny day or sunny weather 5 minutes from now, right? We do this all the time. Now we are going to try to quantify it. How do we show that? If we know knowledge of A happened, we are going to adjust the probability of event B, and we are going to show that with P of B given A, P given A, condition on the fact that A indeed has happened, all right? So let's move on with one very practical example. We know that all of these tests, medical tests, oftentimes they are not 100% accurate, right? So they have very, very high accuracy, but they are not 100% accurate. If someone goes and gets a mammogram, that is a test for diagnosing breast cancer. If that test is positive, what is the chance of getting breast cancer or having breast cancer? All right. So now that I have this information that it has actually happened, that this test result for this specific patient, mammogram test is positive, then what is the chance that, or what is the probability that this patient indeed has breast cancer? This is very different than probability that I had in my mind for someone having breast cancer without that additional information. All right. So there are other tests as well, that other situations. For the sake of time, I'm going to move on. Calculation of probability of B given A. We are going to use this equation for that calculation. Probability that B is going to happen, given that A has already happened, is going to be P of B and A divided by P of A. So these examples, again, I'm going to move on. I hope you are going to take at least time to go over them yourself. These are, we are going to go over them as much as possible in the class. Now that I have that equation, P of B given A equal to P of B and A divided by P of A, well, what is their intersection? P of B and A is equal to P of B given A times P of A, all right? Well, I can also write P of A given B is equal to P of A and B divided by P of B, right? Remember that condition goes in the denominator. Well, P of A and B is equal to P of now A given B times P of B, right? Now I have two equations for finding P of A and B or B and A. They are the same thing, all right? And this is called multiplication rule. Multiplication rule, and that is P of A and B is equal to P of A given B times P of B, or you can write it as P of B given A times P of A. Why are we talking about this? We are talking about this simply because oftentimes a calculation of that intersection is not so easy. So we are going to condition it on something and then use one of these two equations to find that probability. All right. Let me move on. And this is just one example. This is actually, you know what? Let me talk about this because example comes next. Independence of events. Event A and B are independent if knowing one of them does not change the probability of the other one. All right. Which means a conditional probability of A given B, knowing that B has happened, has nothing to do with P of A. It's the same thing. If I know that A has happened, probability of B is not going to change. All right. The funny example that I use in class is define event A as it is raining. Event B is I have a pink car. Right? Knowing that it's raining outside, it does not change probability of me having a pink car. Or if you know that I have a pink car, I don't. But if you know that I have a pink car, what is the chance of raining outside? It doesn't change. That information that I provided you, that I have a pink car, does not change the probability of raining, right? Now, let me move on. Again, these are examples. I hope you are going to take time to go over them yourself. We are going to cover them as much as possible in the class. So I'm going to pause here and record one more video because this is going to be a long discussion.